Okay, good afternoon everyone. Good afternoon. Good afternoon. So we're going to solve a problem today, okay? And then from Wednesday on, thank you. From Wednesday on, we're going to look at Laplace transforms. Okay, so it will be slightly more mathematical in nature. The dynamics boat stops today, but it will resume after some time. Okay, don't worry, you haven't seen the last of dynamics here. Alright, so we have a problem here. Okay, I have two inertial elements, as you can see, two disks essentially. They have moments of inertia J1 and J2. Okay, so these are J1, J2. Okay, the radius of the disks, let's assume them to be the same. They are some capital R or something. Capital R, and once again, please let me know if you cannot see my writing clearly, people in the back and so on, okay? Please remind me, okay, if you cannot see things clearly. So J1 and J2, I have these two disks. The first disk, the disk on the leftmost end, is connected to the wall by means of a torsional spring of stiffness KT1. Okay, the second spring is connecting the two masses, the inertial elements together, as well as a damping element together there. This is CT, K suffix T2, and then I have a series of masses that are constrained to travel vertically, connected by a set of springs. Okay, so I have springs of stiffness K1, spring of stiffness K2. These are translational springs, so they can only move along their length. And then there are two masses, M1 and M2. And obviously the idea is obtain the equations of motion. Okay? So obtain and for many problems that you will see in this semester, it may not be very obvious as to what the physical utility of that problem is straight away, but one can always conjecture. Okay, one can say, for example, if I look at this problem, right? This reminds me of a pair of gears connected by a flexible shaft which is trying to raise a load by means of a string or by means of some other connector elements. Okay, so the strings are modeled as springs. The flexible shaft between the gears are modeled as a set of torsional springs and dampers. And the gears themselves are modeled as two inertial elements. And the loads that they're trying to lift is modeled by means of these two masses. Okay? So that's a physical example. And for more physical examples, we will see in 3360, where you will model real-time electric DC motors, servo motors, and so on, using these different elements. Okay? So wait for the physical appearance of these things, the manifestations of these things. Right now, our aim in 3260 is to use combinations of these elements. Get used to the idea of coming up with the equations of motion. Okay, that's our narrow-minded aim in 3260, right? So to obtain the equations of motion, and I will tell you, this is the way I would solve a problem of this nature. These are the types of figures I'm going to draw in my solutions, okay? And you are welcome to follow the same approach. I use four things. I look at SCP, analysis, static equilibrium position. The second thing I look at is degrees of freedom, which will tell me the number of equations of motion I expect to get from the system. The third thing is the kinematics of the problem. Kinematics is where the struggle happens, because this is where you are closely connected to the dynamics part of your curriculum, ME 2030. I completely understand dynamics is difficult, it's been difficult for a lot of us, but by consistent use of dynamical principles, I hope that it will become much more friendly to us. Okay? And then the last part is the kinetics of the problem, where you look at the free body diagram, kinetic diagram. Okay, so if you want a structure for the mechanical systems problem in 3260, this is a structure. Beyond this, it is anybody's guess as to what we are going to do. Okay, even for certain problems, I do not know what approach I'll take, but it will consistently be of these 4 steps. All right. So I start by drawing the situation at SCP, okay, and I'm going to take the liberty of using this particular figure to depict, excuse me, what's happening at SCP, if that's okay with everybody. Okay. So at SCP, and of course, let's say that there are some torques acting on these things. I forgot to draw them. So this is some applied torque T1. Let's say there is an applied torque T2, so I probably have to draw a new figure for SCP. Let me do that. At SCP, the following happens. I'm just going to redraw the figure. Hang on to it. Don't need to. Alright, so this is the situation at SCP. There are no applied torques. What could potentially happen is that these two masses that are connected together, they could deflect down, right? They're going to travel down because of their weight. So I'm going to call the deflections as, and I'm not going to draw the constraints and so on, forget the vertical constraints. This is deflecting by an amount delta 2. This is deflecting by an amount delta 1. But because the spring of stiffness K1, this is KT1, I'm sorry, KT1 and 2, and CT. Because the spring of stiffness K1 is connected to the disk, what's going to happen is that because the spring is also connected to the mass M1, it's going to be pulled down, and in the process it's going to rotate the disk by a static amount. I'm going to call that angle as theta static 2. But because the other disk, poor fellow, is also connected to this disk J2, then that's also going to be rotated by a different amount, theta static 1. Okay? So this is going to be rotated by theta static 1. Does this make sense to everybody? I'm just imagining what's happening in SCP. Okay? The two masses will plan to move down. In the process, everything that's connected to them will also either move or get twisted or rotated. Okay? And the idea is, okay, first of all, what are these theta static 1, 2, delta 1 and delta 2? How do I even calculate them to begin with? And then, are everything in static equilibrium? Is everything in balance? That's the question that we seek to answer in an SCP analysis. Okay? So let's do that step by step. I'm going to look at the springs first. Let's call this as distance R, okay, all the way to the circumference of this second inertial element. Okay, let me look at the springs first. So spring K2 and K1. So K2 is here. The top end of K2 is connected to the mass M1, so the deflection there is delta 1. Bottom is connected to delta 2. I know there are still people with some confusion here. Look at this, please. If you are trying to capture the force of the spring, here is how you think of it. For positive delta 1 and delta 2, if delta 2 is larger than delta 1, if that is the situation during static equilibrium, I do not know, nobody knows, I'm just assuming it to be the case. If that is the case, then what's going to happen is that this end of the spring will be stretched more than this end of the spring, which will be compressed. Which means that in totality the spring is going to be extended. Okay? So I'm going to have a force on the spring that is trying to capture this scenario, and I'm going to call it as F static 2. Okay? Stiffness is K2, so F static 2 is K2 times delta 2 minus delta. Then I do the same thing for the spring K1. Okay? But I bear in mind that one end of the spring is connected to the disk, and so I look at the rotation of the disk due to the static displacement. This is theta static 2. The spring was connected to the point that I have marked on the disk, as you can see here. That point is being made to move down because everything is connected to everything else. And so we are going to assume that theta static is very, very small, so that this is almost a vertical distance. Okay? So this distance that is being swept, which is r times theta static 2, is approximately vertical, even though this is an arc length. Are we all on the same page? Okay, and this is what is happening for this particular disk. And so the end of the spring that is connected to that particular disk is going to follow the following deflection pattern. This is spring K1. The bottom of it is connected to the mass M1, so that's going to be deflected by an amount delta 1. The top is connected to the disk, and so that's going to be reflected by an amount r times theta static 2. For positive delta 1, positive r times theta static 1, if delta 1 is larger than r theta static 1, I'm sorry, static 2, then what you can say is that this spring is also in extension at SCP. Okay? F static 1, and F static 1 can be given as K1 times delta 1 minus R times theta static 2. All right, I hope we are all on the same page. I'm going to save time for questions, so hang on to your thoughts. I will come back to you. I appreciate your understanding. Okay, I want to finish this thought process. Then I look at these springs. The damping elements, do I need to worry about damping elements in SCP? I don't need to, because they don't have any restoring force, they don't have any restoring torque. You know, for all the reasons that we have discussed in the past. Damping elements only exert a restoring force or a torque for a velocity, not for a static displacement. Okay, static displacement, if you differentiate with respect to time, is 0. Okay, there is no static velocity. It's an oxymoron. So I look at the springs. This is one. This is the other. Okay, I first draw out the theta static 1 and theta static 2. So let's do it for this spring first. This is theta static 1. The other end of the spring, KT1, is connected to the wall, so nothing special happens there. Here, theta static 2, theta static 1. Is this really what's happening? I don't know really. I'm just assuming that if this is the situation, this is how the system is going to behave. And I calculate my findings accordingly. Okay? So I look at this one first. We've done this in the last class. Okay? I can focus on either one of these ends. I focus on the end where it is most convenient for me. I look at this here. I apply a torque to cause that deflection. This is T static 1. Okay? Equal and opposite torque. T static 1. Okay, let's call this as wall W. This is end O1, which is connected to the first ring or first disk. Okay, this is O1. This is O2, which is connected to the center of the second disk. Okay, and likewise, I focus on one end. This is T static 2. Can focus on either ends, no harm done. Okay, then I'm going to have an equal and opposite T static 2. Okay, that's a good catch. Right. Then I write out the formula for the deflection of the springs. Okay, so this is now T static 1. There is not much thinking in this because there is only one angular deflection, so it's the stiffness times the angular deflection. Alright, then I do the same thing for this guy. KT2. As mentioned in the last class, here is how you figure out what's going on. Theta static 1, theta static 2 are in the same sense as drawn, which means that theta static 2 is actually helping me as I'm trying to twist this end of the spring. And so I have to subtract the effect of theta static 2 when I'm calculating the torque at T1, at the other end O1. So this is theta static 1, theta static 2. In my lecture notes that I posted last class, I have a detailed explanation of this logic. Okay, so if you still have questions, happy to answer it at the end of class. Alright, so this is the second torque, static torque. With your permission, I'm going to draw the discs right here. Okay, so I have the first disc. Second disc. Do you guys have a question there?
Is that the static spring force?
I don't know. It's called a torque, so it's not a force. Okay? So if I now draw the free body diagrams, okay, and I appreciate your understanding. If you have any questions, please talk to me. I draw the free body diagrams at static equilibrium position. Okay, this is the end O1. This is connected to that particular end, so I'm going to have an equal and opposite torque back on this body here. This is T static 1. Now this torque T static 1 is called as a restoring torque. That is, the disk that was connected to that spring is trying to rotate it in the sense of theta static 1. And so the spring that is connected to that particular disk is trying to prevent it by producing a restoring torque. That's what is the name for it. Okay? So this torque that you see here is the effect of the spring on the body. And that's the restoring effect. The torque or the force that you see on the spring is the force or the torque exerted by the masses on the springs or the dampers. Okay, that's not the restoring torque or the restoring force, but their magnitudes are the same. Okay, so that's one. This end is also connected there, so this is end O1. There is equal and opposite T static 2 here. This is the end second disk O2. Okay, I'm going to have the torque from the end O2 equal and opposite to that. So this is going to be in this manner, I believe. This is T static 2. Okay. Do not forget, one end of the spring is also connected to this disk, which means that I'm going to have an equal and opposite force to what I had drawn on the top spring there. So that's going to be F static 1, but pointing downwards. And the distance is R, and if you want, you can draw this figure this way. Okay, this is an equally valid representation of that figure. Okay, if you want it for simplicity. Then I draw the free body diagram of the masses at SCP. Okay, the two masses, they're fairly straightforward. weight. I have spring force, F static 1. Okay, and then the end mass M1 is connected to the top end of the second spring, so I'm going to have a force F static 2 pointing downwards. Likewise, the second mass. M2G, F static 2. And all I have to do is just sum forces, sum moments. It's a fairly straightforward exercise, okay? And I'm going to write down the results from it. Okay, so for this first mass, I'm just summing forces up. Nothing special, this is basic statics. So I'm going to have M1G plus F static 2 this is equation 1. Okay, this is from the first mass. Then from the second mass that I've drawn, as you can obviously see, F static 2 is equal to M2G. There are no applied forces, there are no applied torques because this is at static equilibrium position. Minus M2G is equal to 0. It's either M2G minus F static 2 is also equal to 0, same thing. Then that's from here, here. From here, if you want, you can draw the circle view. This is the torque, T static 1, T static 2, that's O1. If I sum the torques about the point O1, basic statics, both the torques are acting in the same sense, so I'm just adding both of them up and setting them equal to 0. Okay? Hang on. Yes.
So, which direction is theta static to static?
Oh, yeah, sorry. So this is T static.
So then how?
So theta static is the same sense. It's just assumed to be in the same sense as theta static.
So then, how come for your free body diagram at the bottom you have theta static to down?
It is equal and opposite to this one. Right? So this is equal and opposite to that one. Right. Does this make sense, or am I making a mistake? I think I'm okay. We can talk later too. Yes, question?
No, you're figuring out.
Okay. They're equal and opposite. They have to be equal and opposite. So if the sense makes, so this guy is equal and opposite. Okay. So if I look at it this way, for example, if you view it this way, this comes across as what? As a clockwise torque, which means that has to be counterclockwise there, right? So you're probably right. It has to be counterclockwise there. I just want to make sure that's the situation. So this is F static 2. This is T static 2. So you can look at it this way. Okay, if you're looking at it this way and you're looking at this arrow here, this comes across as a clockwise rotation for me, which means that back on the mass or the inertial element, it has to be the opposite sense. Okay, it has to be counterclockwise, which is what it is drawn here. Thank you. All right. So this is now the fourth one. Sum of moments about the point O2. As you can see, there's a torque due to the force F static 1. So that's going to be both of them in the opposite direction. Times R. Equation 3. Okay, so equation 3, 4, 1, 2, save them. We are going to make use of them when we eventually do the kinetics of the problem. All right. I'm going to take some liberties and use this figure for the kinematics. And we're done with the ACP. those equations will all eventually vanish. Why are we doing it then? Is just to ensure that everything is in static equilibrium. Okay, that's our only purpose here. Okay, then the degrees of freedom. We have always assumed that if you see an inertial element, it is acting as if it's pinned at its center, so it has only a rotational degree of freedom. Okay, so I'm going to assume that theta 1 and theta 2 are the degrees of freedom for the two inertial elements. So theta 1 of t, theta 2 of t are the degrees of freedom for the elements J1 and J2. Okay, so this is for J1, this is for J2. Then the two masses, it's fairly trivial, they're just going to have vertical motion only because they're constrained, and this is all a planar problem. So I'm going to have two other degrees, y1, y2 for the masses m1, for the masses m2. The important thing is these are all prescribed from ACP. Okay, so all degrees of freedom from ACP. Then we look at the accelerations. This is fairly trivial for this problem because there is not much of the pendulum effect, or there is no rolling without slip and so on. Okay. So for this problem, and we've already looked at such problems in the past. So I have theta 1 double dot, theta 2 double dot, and y1 double dot, y2 double dot. All I have to choose is a positive sign convention, and then I'm on my way to calculating the kinetics of the problem. All right. Let's do that here. The idea is exactly the same as that in SCP. Hang on, let me draw the kinetics and let me get the angles, sign conventions and so on. Okay, so sign convention. Alright, I'm drawing them from ACP, so which means that for me, I have to draw the net effect of them. Assume this way. Assume this way. So this is going to be theta 1 plus theta 1 static, theta 2 plus theta 2 static. This is a net reflection. Theta 2, I'm sorry. And likewise here. I'm also once again drawing the net deflection of the masses, so that's going to be y1 plus delta y2 plus delta 2. You are welcome to draw only y1, y2, theta 1 and theta 2 and then say they are all marked from ACP. That's also completely fine. Okay? So that's another way of doing it too. Both of them will end up with the same results. Then I'm going to have the torques acting. And I have the spring here. I have the torque T2. And that's about it. Question. So here is a design problem. Okay. If I replace this torsional spring by a torsional damper, would it be a valid problem? So if I replace this torsional spring by a torsional damper, would it be a valid problem? So I see a lot of people saying no, and the answer is yes, you're right. It's no, it's not a valid problem. This is because if I look at the free body diagram of the element right there, which is figure 3, I would not have a T static 1, but I would have a T static 2, which means that the figure is not in equilibrium, and so that means that you cannot have a situation like that. To start off with, I have to have everything at rest. Everything has to be balanced at rest. If it is not at rest, then how am I going to do anything? Right? So you cannot have things in equilibrium. You cannot have things in accelerated motion to begin with right away. Static starts first. Yes, question?
So then, for any dampering element, any functioning dampering element, can you not have it like by itself at all?
You can have something like this, because in static equilibrium, this spring carries the burden of maintaining static equilibrium. But if I got rid of this spring and I put a damper here, but I still kept this spring, would it work? It would not work, because I would not have any restoring torque to the force of the spring here from static equilibrium. Okay? So these are all ways in which you can think, okay, how can the problem be changed? How can the problem be asked? What if I got rid of this spring? Would it be a valid problem? No, it's not going to be a valid problem. Okay? What if I take a damper and replace this spring with a damper? Obviously not a valid problem. Okay? What if I put a damping element here? Would that be a valid problem? Not in addition to the spring. I got rid of the spring here, I put a damper there. What would happen there? Yes?
No. No, because a damper can't support weight.
It cannot support weight, but you see the weight of this could be supported by this spring.
But not the whole system.
But you see the problem, what you're referring to is the T static 2. That would no longer be there, you see. So it is completely fine if I replace this by a damper. Does everybody see that? So if I replace this by a damper, what could happen? I'm thinking out aloud, okay? Maybe I don't know the answer myself. If I replace this damper here, if I replace this by a damper, there is no force acting on the mass right here, okay? Now, is this going to be torqued? Not by this, but is it possible that there could be a torque due to this element here? Yes or no? Once again, my question is this, okay? Just to be on the same page. I get rid of this spring fellow, I say put a damper on. Put a damper on things. What happens? Yes.
Mass 1 and mass 2 just fall.
Mass 1 and mass 2 will just fall, but this mass is balanced by this spring. This mass is balanced by that spring too.
And circular reasoning works because circular reasoning works.
In some ways. So essentially this system is not connected to this system at all in static equilibrium. That's what you're saying. They are two independent systems. So does this mean the problem doesn't work? I mean, you have two systems in static equilibrium, suddenly you start putting forces onto it, it becomes a single system. So technically it could work, but it makes no sense. It's complete garbage. Okay? Technically it could work. I could have two systems. I could say, okay, everything is fine in static equilibrium, but it makes absolutely no sense. I'm having this fellow floating in free space. I'm having this fellow floating in free space. What's the point? Okay, so be careful if you're assuming certain things to be replaced by certain other things, and that's precisely the design questions that you will face when you go to a job. Okay, the cost-benefit analysis of employing a damper is better than that of using a spring. What do I do? Where do I replace it with? Okay, what are the locations I could find out? Right, so something to think of. All right, let me complete this problem and come back to questions. Let's see. I need to perform the kinetics of the problem, and in many ways the figures are the same as what we did for static equilibrium. So let me draw the springs first. One here, one there, the wall, O1, O1, O2. This is O1, okay. Then I have theta 1, theta static 1. Just for simplicity, I'm going to draw only theta 1, okay, because we know theta static 1 is going to produce a torque T static 1. Then I'm going to have the same deal here. Theta 1, theta 2. These are all drawn from SCP. Okay. I draw the torques as indicated earlier. This torque is going to be T1, but I have to include the T static 1 from before. Then I'm going to have the same story there on the other side, equal and opposite. Okay, this is going to be T1. I'm sorry, this is T2. Apologies. T2, T static 2, and then likewise I have the torques drawn here. This guy is T1, T static 1, equal and opposite. T1, T static 1. And one can also draw the free body diagram of the springs. I'm going to take the liberty of using ideas from SCP. So this is Y1, Y2, and then the spring of stiffness K2. Forces F static 2 and F S2. Likewise, Fs2, F static 2. This equation remains similar to what you had in SCP, except that now you're going to have y2 minus y1 instead of delta 2 minus delta 1 for Fs2. Okay? So Fs2, if I can write it here, K2 times y2 minus y1. Do my figures make sense to everybody? Is everybody able to discern where I've drawn everything? Is it confusing for people? All good? Any questions so far? Question?
Is there any equilibrium on K1?
Equilibrium, I'm going to draw the figure here. I haven't drawn it yet.
Oh, okay.
Yeah.
And then also, one more question. Is it just safe to assume that like whenever a torsional element is applied on either O1 or O2, that it flips the sign based off of each particle that it goes through? Like for example, like if it's on the right side, if it's on the left side of the spring, KT1, it'll flip for O1, and then it'll flip again for KT2.
Yes, of course, because what you're doing is using Newton's third law, right? Every action has an equal and opposite reaction. So every time you draw an element, whatever you draw at the end of one element has to be equal and opposite to what you draw on the next element. Okay? So this torque, as you're saying, will be equal and opposite on the disk O1. Okay? But it will be the same sense here. This is a different effect, of course. It's not the same torque carried forward. Alright, I'm continuing here for the first spring. This is Y1. This is theta 2, okay? So I'm going to have the radius times theta 2 as the displacement of the top end of that first spring. That's going to be this amount here, r theta 2. R theta 2 assumed to be approximately vertical because we're looking at small angles. This is in tension for y1 greater than r theta 2 and y1 greater than 0. R theta 2 assumed to be 0. Likewise, this is in tension for y2 greater than y1. Okay, that was the second spring. And I have the forces written as follows. This is Fs1, F static, and likewise equal and opposite on the bottom. And Fs1 is K1 So that's that. Then I have T1 and T2 written the same way as we wrote for the quantities at SCP. So T1, okay, T1, theta 1, T2 written based on the way it is drawn here, theta 1 minus theta 2. All right, so that's all the force balances for the springs, and then we have to draw the masses themselves, draw the kinetic diagrams, some moments up, and that's pretty much it. Okay, this is a cut and dry procedure for torsional elements. Yes, question.
What about the damper?
Oh, the damper. Thank you. I forgot about it. You're putting a damper on my enthusiasm. As I mentioned last class, dampers, they follow pretty much the same procedure as you do for springs. Okay, so which means theta 1 dot here. Theta 2 dot. Then I have the, this is end O1, this is end O2. Okay, and then I have the torques, TD, equal and opposite, TD, and TD, CT, theta 1 dot, theta 2.
For your
Yes, yes, question.
Do you have to assume something about whether
The-
negative 2 dot is greater than beta 1 dot, or vice versa?
Not necessarily. Not necessary, because it's drawn the way it is drawn here. That's it. So if I had looked at it from the other side, I could have drawn TD in the opposite sense. If I looked at it from O2, I would have drawn it in the opposite sense, but my torque would be theta 2 dot minus theta 1. So it is implicit in this way. Yes, yes.
For your equation for FS1 up there, should that be a theta 2 instead of a theta 1?
FS1, you mean?
Yeah.
Where is that?
on the top, it says Y.
Oh, yeah, yeah, this is theta 2. Thank you, thank you. This is theta 1. That's not right. Where is FS2?
On the top, FS1 equals K1 times R. Y.
Oh, yes, thank you, thank you, thank you. I think it's too late. You're making me do things here. You're a tough crowd to please. All right. So I think we are in a good position here. I'll take care of the two masses, inertial elements first. Then we'll just write the equation for the masses, okay? So start with the first inertial element. Now this is in kinetic or in motion, okay? So there is time varying torque acting on it. This T1 of T. This is O1. Okay, and the O1 was connected to the damping element as well as the spring element, which was drawn right there. So I'm going to have two torques. This is TS1, T static 1, okay, or T1. I guess let's call it as TS1 because T1 is the torque. I'll just keep it T1. And this is this is the torque. It's too late to change it up there, okay? So this is the situation here. Then TD, that's the torque from the damping element. And that's about all I have for the first inertial element, and draw its kinetic diagram as well. This is J1, theta 1 double. All right. Sum of moments about the point O1 will give me the equation of motion. The static torque, I have one more torque that is missing. I have to draw Ts static from 2, okay, so that the sum of Ts1, static 1 and 2 cancel off as we have written out here. So sum of moments about O1 on the kinetic diagram. Assume a direction for the moments. Okay, so clockwise, positive. Clockwise, positive. If you want, you can draw them as two-dimensional circles, completely fine. If I look at all the torques acting on the free body diagram, I have T1 function of time. Okay, this is the applied torque. Then I have the rest of this entire bunch here. I'm going to have minus Td minus T1 minus T static 1 minus T static 2 is J1 theta 1 double dot. From arguments of static equilibrium, using equation 3, T static 1 plus T static 2 is 0, so the static terms will disappear as expected. Okay, this is coming from SCP analysis, right? Write the equation of motion, bring all the necessary terms onto the necessary side. So I have J1 theta 1 double dot. Then I'm going to have T1. I'm going to have a T2 as well. I forgot about that. I'm sorry. It is connected to the second string. So I have it in the, where is the second string? It's connected this way. So this is also a T2 plus a T2. Minus a T2.